in this section, we're going to look at real batteries, how real batteries work, and how they apply to different functions of everyday life.
So if you're looking at using non-rechargeable batteries, generally they are these alkaline dry cells. What we have is a zinc anode, and the wire that basically transfers electrons goes through that zinc anode. And then as the reaction runs forward, it transfers electrons through that wire to the manganese on the other side. So in the process of transferring electrons through the wire to the manganese on the other side, that forward motion of electrons is what drives your electronic devices. In this case, this is a Discman, which is a device that has not been used since, 15 years. But nonetheless, this is pretty much how all alkaline batteries work. It's the forward motion of electrons that gives you energy. And it was worth mentioning that if you've ever had a battery that kind of exploded or went ugly, and you get all this white powdery junk, that's probably zinc. It could be manganese, I guess, as well, but it's these metals that are coming out, that are kind of ruptured the cell and are coming out that you see on the side. This voltaic cell reactions also explain corrosion a lot. So if you just have iron and oxygenated water, you get positive 0.8 volts, which is a pretty good voltage, right? It's not bad. And so, if you have some oxygen, you get some voltage out of this process. However, if you have acidic ions in there, we go from 0.4 volts in the cathode to 1.23 volts in the cathode, which is dramatically more spontaneous and also going to be dramatically faster as well. Again, the thermodynamics and kinetics are not necessarily connected, but huge concentrations of the H+ ion do affect speed, and so the more acidic your water is, the more reactive this will be. And this is why acid rain is so bad for metal, right? So bad for iron, is it dramatically increases the voltage and dramatically speeds up this reaction. Now, what you can do with iron is you can galvanize it. When we say we're going to galvanize iron, what we're going to do is really cover it with a surface coating of zinc. Now, because the zinc anode is more spontaneous than the iron anode, we are always going to do the most spontaneous reaction first. So the zinc reacts first, and then only when the zinc is completely gone, the anode will react next. And so, we can erode this zinc, and if you want to at some point, you can re-galvanize the steel if it's important. Most of the time, once the metal actually starts to rust, we just throw these things away. When we talk about electrolytic cells, these are cells that can not only run forward, so, we have a copper cathode, the reaction moves forward, we get a positive voltage. But in an electrolytic cell, after the cell is run far enough forward and we can't get voltage out of it anymore, we can actually apply a voltage and make this go backwards. At this point, we're kind of pushing electrons into the system, we're pushing work into the system. That is going to make what was the anode is now electrically charged, and the cadmium is going to start to acquire back onto the cathode again. The copper is now got a positive charge, and we're going to see that copper reform into copper ions as we drive these electrons backwards. So electrolytic cells are essentially rechargeable batteries. And so they're extremely important for that reason. We just have to know that the anode and cathode switch places, and this works. So you're driving this reaction forward, this non-spontaneous reaction forward, by applying energy. So if you buy rechargeable batteries, like we have a bunch of Eneloop batteries on them, if you look at the label on the back, they are almost always NiMH, nickel metal hydride batteries. And so this uses two different sets of nickel metals with hydroxides. It's a nickel oxide hydroxide on the cathode side, and then a nickel hydroxide on the product side. So that seems weird. Why would you want to do that? Well, when you run the cathode forward, right, it creates hydroxide. When you run the anode forward, it uses that hydroxide to create the nickel metal. So our electrolyte solution is also hydroxide. And so what that means is as the reaction moves forward, we're simply moving hydroxide from one side to the other. Again, the voltage is traveling through the wire that creates the incentive to do this. And of course, as the electrons travel through the wire, that gives our machines energy. Now, the brilliance of this is that because all of these reactions run on the same ion, when you push energy into this battery, right, it's going to force this reaction to go in the other direction. So the pure nickel metal reacts with water and it gives hydroxide back. And that it's forced to do that because of the electrons pushing themselves into this reaction. So the hydroxide goes back across the electrolyte solution and it reacts with the nickel hydroxide to create the nickel oxide hydroxide. Okay, so the reactions itself are very complicated, but the idea is very simple. Every part of this can be recharged, but the other parts, such as giving this energy, it goes in the non-spontaneous direction. Now, when you look at lithium-ion batteries, which are inside your cell phones or your iPads or any real gadget you have now, what you're looking at is not really even a reaction. It's lithium inside of these cages. Now, carbon doesn't really want the electrons it has. And so when lithium ion is in these cages, the carbon atom can be thought of as kind of loaning its electrons towards these lithiums. So even though it's still a lithium ion, it looks more like a regular elemental lithium. Now, when you apply incentive to this reaction to go forward, you basically connect these two cages with wire. The lithium ions transfer out of the carbon cages and into the oxygen cages. Now, of course, oxygen is attracted to those electrons, it pulls them off, so now this lithium feels much more like a lithium ion. And so even though we are not technically changing from lithium metal to lithium ion, to the lithium ion, it feels that way. And so we still get a massive voltage somewhere around 3 to 3.6 volts per reaction, which is a huge, huge voltage. And that's one of the problems with these. Even though there's a lot of energy, you do have to worry about overheating because of the amount of energy they get off and the energy heat released as we change between these cages. And of course, when you want to run this reaction back, when you pump energy into it, the lithium is forced to leave this oxidation cage and go back to the carbon cage. Now, these batteries do a really good job of recharging without flaw. Again, anytime you have more chemical reactions, there's more incentive for these things to fail. But what is going to happen the more times you charge your phone is that these cages are not going to fill up linearly, right? We're going to get a lithium ion that gets stuck somewhere, or a lithium ion that gets lost, or a cage that just isn't filling in the right order, so we're missing some of these cages from refilling. So the more time you run these reactions, the less and less yield we are going to get out of this reaction, which is why your battery lasts less and less long. So when you talk about car batteries, most car batteries are still lead rechargeable cells. And you think about the poison that is lead and what it does to brain chemistry. This is a terrible, terrible idea. But nonetheless, this is what you have. It's also why if your battery cracks, you really want to take care of it right away. I had a battery that cracked in bad weather in Boston, and it basically, the sulfuric acid leaked onto my alternator and was basically a $400 repair. Anyway, so we basically have a solution of sulfuric acid. And then we have these alternating electrodes, one of them has lead and one of them has lead oxide. So as the lead moves forward, it reacts with any bisulfite created from the sulfuric acid, and it makes lead sulfate. Whereas the lead oxide reacts with all the acid and creates lead sulfate. So we're essentially creating the same product on both electrodes. And then every time you run your car, right, the energy coming out of that car forces electrons back into this process, which shifts the whole reaction backward. So both electrodes change from lead sulfate based on where the electrons are going. They either change back to lead or back to lead oxide. So you can recharge this over and over again. What's going to happen as you run that car battery more and more is some of that lead sulfate is going to end up in the bottom of the car battery. You're going to end up with kind of a lead sulfate sludge, and these electrodes are going to get smaller and smaller. And as that happens, you will have less ability to recharge that battery, and if that recharge gets small enough, eventually you won't be able to turn your car on. Now, one of the fuel ideas that's been pushed pretty heavily is a hydrogen fuel cell. This is a brilliant idea, but there are some problems, as we'll talk about. So basically, you would push hydrogen and oxygen into this fuel cell. They would mix at some kind of catalytic spot, and you would get out water, right? So this is a very spontaneous voltage at 1.23 volts. The reaction itself would be super cheap. It would be renewable. It would be, easy to run. The problem is getting hydrogen to interact with oxygen in a steady way. And to do this, we use a platinum catalyst as the standard form. And the problem with platinum is that it's one of the most expensive and rare metals on this earth. So, they say, well, these cars that use hydrogen fuel cells only cost, $200,000. The problem is, the more of those cars you make, right, the less platinum you have. And so if you tried to make a fleet of these cars, the platinum cost would skyrocket. So until we come up with a better catalyst that's cheaper, and they're working on things with iron and other cheap metals like nickel, but they just haven't got the efficiency high enough to make this worthwhile.